this is for like a single step in a reaction mechanism, the reaction of a single molecule or group of molecules, same transformation. The rate of that reaction depends on the activation free energy, how high you have to go up to get to the transition state, and then it depends on a host of other factors, including temperature, and then these constants. So, and we talked about how if you plot the natural log of the rate constant times Planck's constant over this term kappa, which is often assumed to be close to 1, the Boltzmann constant and T, and then you plot that versus 1 over T, your slope, I don't want to get this wrong, is the opposite of enthalpy, and your intercept is entropy over R. So enthalpy over R, entropy over R, you can get a sense for how much of the free energy comes from enthalpy versus entropy. Now, this isn't the only approach chemists use to talk about reactions, and in fact, Arrhenius theory predates the Eyring theory, and this is related to sort of a macroscopic rate constant. This is for a process that may involve many steps, but just overall, what do the kinetics depend on? And the Arrhenius approach has actually been used, I think I read, to you can plot the rate of cricket chirping versus temperature and get out an activation energy for that process. And it happens to be about the same as on the same increment of activation energy you'd need for an ATP-based reaction, which is kind of interesting. But in any case, for the Arrhenius, we're going to say the rate constant equals some pre-exponential factor, then exponential minus energy of activation over RT. This is just active, it's not free energy, it's just called activation energy, and it represents for a whole process rather than an individual step. Okay, but you can do the same sort of thing with Arrhenius as you can do with the transition state theory. That is, if you take the natural log of K, then you're going to get this. And again, the slope of that plot of natural log of rate constant versus 1 over T should tell you something about the activation energy, and you can even figure out what this pre-exponential factor is, because that should be the intercept. So for a lot of processes, if you want to learn about activation energy, you need to vary temperature. So when is this useful? I need to get a graph or a figure from a previous iteration of the course that I didn't paste over here yet, but it's kind of interesting. So this is an Eyring plot. On the y-axis, you've got natural log of rate constant times Planck's constant divided by Boltzmann's constant times temperature, and then they're plotting it versus 1 over T. So we're using here an example of Eyring transition state theory analysis. And the idea is they were doing a reaction, they were monitoring the rate of reaction in which the cobalt-carbon bond in vitamin B12 is cleaved by an enzyme. And the precise identity of the enzyme isn't important for what we're going to talk about today. But one of the things they saw is an Eyring plot that's not linear across all temperatures. You see how we have one slope here, and then it's like it changes, and another slope there. You sort of have two linear domains, and they have different slopes. What does this mean? Well, when you see curvature in an Eyring plot, it usually means that there's some change in mechanism, because in order to change the slope, you have to have changed the delta H of the process. You have to have changed the activation energy fundamentally. One thing that confuses me about these plots of 1 over T is that higher temperature is located near the, right? Higher temperature should be smaller values, and then lower temperature should be higher values of 1 over T. So what does this suggest? At higher temperatures, remember, slope has to do with activation enthalpy. So the slope is lower here, so this is lower activation enthalpy, and then it's higher here, the slope is more negative here, that's higher activation enthalpy. And the change is around 30 C. And the authors interpreted this as saying that below 30 C, there's something else that has to happen before the reaction can proceed. And they rationalized that by evidence that the enzyme actually, its most stable conformation below 30 degrees is an inactive form. So in order to catalyze the reaction, it has to change its conformation first, which requires energy, and then catalyze the reaction. So that extra conformational change is built in. I'm getting confused again. You see how I did that? I was thinking lower temperature to the left. That's a really hard habit to break. At lower temperature, activation enthalpy is higher because you have to change the folding of the protein first and then do the reaction. So you can learn some interesting things from these kinds of analyses, and you may see this in different contexts in the future if you're reading papers. Why would you want to know about activation, enthalpy, and entropy anyway? Let me show you a table that's from your text that shows some entropy values from commonly known organic reactions. This is kind of interesting. We often, at least in undergraduate organic chemistry, ignore enthalpy or entropy because it's hard to think about. So we pretend that the enthalpy change in a reaction is negligible. But this table in your text, gives you maybe a better sense for what some of these values are. So first, these are activation enthalpies. What the heck is an entropy unit? Well, entropy, unfortunately, is measured in calories per mole per Kelvin, usually. I don't know why, but that's the typical. So that's an entropy unit. Absolute values are not important here. I prefer to combine entropy with temperature to give you T delta S, which is you can compare directly to enthalpy, but that's just me. In any case, we can compare sort of the relative values of these various processes. Remember here that negative values for entropy means that you're having to lose entropy, lose disorder, become more organized. So it's interesting to note that for reactions where you have to bring two things together, the activation and entropy is negative, right? This is just nucleophile attacks carbonyl, and that requires two things. It's interesting to note that a similar reaction, opening of an epoxide by a nucleophile, has much lower activation entropy. Why is that the case? I don't know, but you also have to think about what solvent is doing, how solvent impacts the transition state, because you can imagine some transition states requiring solvent to be more organized versus less organized, and so it can get confusing. Entry 3 here seems to follow what you would expect. In this reaction, you're taking one molecule and turning it into two. You're hydrolyzing this glycoside, kicking off the methanol group. So in the transition state, you presumably you're going from something that was one thing into something that's almost two and therefore has more degrees of freedom. So that's actually a favorable activation entropy. This is a typical SN2 reaction in entry 4. Again, very unfavorable activation entropy, which you would expect because you got to have two molecules find each other. And then conjugate addition is maybe not surprising. Lastly, peroxide homolysis. This is just breaking of the peroxide bond to give two alkoxy radicals. That has a favorable activation entropy because, again, you're taking one thing and making two. So you can actually assess these things, and they tend to track with what you would expect, and that's kind of nice to see. All right, so that's maybe enough of the transition state theory and entropy versus enthalpy. We're going to spend the next little bit talking about postulates, rules of thumb, aphorisms that we use in organic chemistry to rationalize changes in reaction rate with, say, changes in the structure of a starting material or a product. So, first principle is, see if you like this, the Hammond postulate. Ever tried explaining this to somebody? What the heck is the Hammond postulate? It's what wealthy investor John Hammond decided when he wanted to try resurrecting the dinosaurs in Jurassic Park. Is that? I gotta try better. Reference to a movie in the 90s probably will fall flat. Okay, but seriously, what is the Hammond postulate?
It's a postulate that talks about the transition state. It talks about how fast you can form the transition state will help in determining how fast the rate of reaction will be.
Okay. It's related to the energy of the transition state, and it tries to connect that energy of the transition state to energy of starting materials or products. And the issue is this. Often we're going to want a way to rationalize differences in reaction rate with differences in starting material structure or product or intermediate structure. And the Hammond postulate is a way to do that, to rationalize changes in rate, or in other words, transition state energy, by connecting the transition state structure to either the starting materials or the intermediate / products. Okay? So the basic tenet of the Hammond postulate is this. On a reaction coordinate diagram, two adjacent positions that are close in energy are necessarily, how do you spell that? Two C's. I always get that wrong. Necessarily similar in structure and geometry. Okay, and the rationale for that is on a reaction coordinate energy diagram, on the x-axis we have some, it's called the reaction coordinate, but really this is some geometric change that correlates with the progress of the reaction. So if I have an energy diagram that looks like this, starting materials, transition, and products, I'll look at this and say, okay, the transition state is closer in energy to the starting material than it is to the products, which will mean that there's less of a geometric rearrangement to get from starting material to the transition state than there is to get from the transition state to the products. So in this case, because the transition state and the starting material are close in energy, we infer that they are more similar in structure than the transition state and the products. Okay. Now, some people will use some terms to describe the Hammond postulate. For example, when the transition state resembles the starting material, people will say it is an early transition state. What they mean by that is it's early because it more closely resembles the stuff at the beginning than the stuff at the end. All right, so if you hear that, that's just what people are talking about. The classic example of a late transition state is the SN1 reaction, where the energy diagram looks like this. Here's reaction coordinate, which is really just some geometry that describes the progress of the reaction. Here is energy. You go from starting materials here through a high energy transition state to a carbocationic intermediate and the leaving group, and then you have the nucleophile come in, and then you have your product, right? Here is the rate determining transition state. Here is, I was an unfortunate choice as a leaving group because I want to use I as an intermediate. So let's just use an alkyl bromide. I is your intermediate. So in this case, for this rate determining step, the transition state is closer in energy to the intermediate. We can't measure or ever see the transition state, but we can measure and detect intermediates. And so, because the transition state is closer in energy to the intermediate, we're going to say the transition state resembles the intermediate in geometry and structure, more so than it resembles the starting material. We would call this, some people will call this, where the transition state resembles the intermediate or products, as a late transition state. All they mean, it's late because it resembles the stuff at the end more than the stuff at the beginning. And it's late with respect to this first rate determining step. Yeah?
So we don't have a situation in which, like, the transition state resembles the products, it's the intermediates.
Well, that's the most familiar example I was able to come up with. You can envision a reaction that's uphill and looks like that, and that would be the same sort of thing. In this case, yeah, transition state would resemble products. It's just harder for me to come up with an uphill reaction like that off the top of my head. Now, one thing to realize is that the Hammond postulate is a rule of thumb. Go ahead.
And so the first instance will look more like an SN2 reaction.
Right. Yeah, the first example would look more like an SN2 reaction. And in some cases, the transition state is neither close to the starting materials or the products, and so it might be somewhat different in geometry than both of them. So this is not a hard and fast rule. It's a general idea. And it doesn't apply in all cases because there isn't any fundamental reason why the transition state has to be similar to the starting materials or the products. Your text gives some weird figure, which maybe I'll try to show you here. I wonder if I can select more than one. Probably not. Your text gives you a situation where the Hammond postulate clearly doesn't apply. because, and it's hard to, they should have used different colors here. It's sort of hard. We have the same same energy starting materials. Here is a transition state that's highest in energy, but it leads to a product that is not highest in energy. Here is a transition state that is not highest in energy, but it leads to a product that is highest in energy. So this is a case, let's see, let's highlight one more. This is one where the transition state is lowest in energy, or not lowest in energy, rather. It's almost lowest in energy, and it leads to a product that is lowest in energy. So there doesn't have to be a connection between, for a given reaction. And what do these curves represent? These curves represent related reactions where we have changed the structure of the starting material such that there are changes in the structure of the transition state and the product. And in this case, changes in the transition state are not necessarily reflected in the changes in the product. So it doesn't have to be the case. Do I have a specific example where it's not the case? No, sorry about that. But where you would use this principle is just like you've taught or learned in 351 to explain why, say, this alkyl halide reacts faster than this one versus this one in the SN1 reaction, fast, slower, no-go. And that's related to the stability of the resulting carbocationic intermediate, which is okay, less okay, and offensive. Not in the gas phase, but in solution, kind of a problem. Right, and so we would predict that a starting material that has to go through proceeds to an intermediate that is higher in energy will necessarily have to go through a transition state that's higher in energy because the transition state resembles the intermediate in structure. So I understand that's kind of nuanced because I just told you that it applies, but not all the time, and I didn't really give you the tools to understand when it doesn't apply. But my purpose is not to cover every possible situation that you might encounter, but just give you the language that organic chemists use, and then understand when you're reading a paper if you'll know what they mean when they're citing the Hammond postulate, and you'll know what they mean when they say, interestingly, this doesn't follow the Hammond postulate, and you'll understand why that's interesting. Questions about that? Okay. A related rule of thumb, and it's sort of derived from the Hammond postulate, is what is called the reactivity selectivity principle. And this one maybe applies even less than the Hammond postulate does, but you will hear people talk about it. And the idea is this: more reactive reagents are less selective in terms of where they will react. The analogy I can remember years ago that Dr. Savage gave is that suppose you have a refrigerator and in the back of the refrigerator is like a delicious chocolate cake, and in front of the refrigerator is some broccoli. If you are absolutely starving, you may actually eat the broccoli first because it's right there and you just are anxious to get something in your mouth and swallow it. Whereas if you're less hungry, you may choose the chocolate cake. Now, when I heard that, I sort of think it should be switched, because if I'm not starving, then I can think clearly and maybe I'll make a better choice versus, but at that point the analogy breaks down, so we don't worry about it anymore. What's an example of the reactivity selectivity principle? Well, consider radical alkane halogenation, and consider the following substrate, which has tertiary, primary, and secondary carbons. Shoot, I don't really have the best. Well, okay. Radical halogenation just in terms of the mechanism, proceeds via the following type of mechanism. You've got first hydrogen abstraction to give a radical intermediate. Oops. And then that radical intermediate, then reacts with another halogen to give you the product. Now, of course, let's see, you would notice that because there are different carbons here, we have the possibility of regioisomers, right? We could react with the secondary carbon or one of the primary carbons. So there's a regioselectivity issue, and it has been observed that radical bromination, and we'll just put it in terms of numbers, and this may be general instead of just for this substrate. So selectivity here in terms of ratio of tertiary to secondary to primary when you've got the choice. Presumably this is corrected for statistics because, of course, in this substrate you have 3 primary carbons versus 1 tertiary and 1 secondary, so you sort of have to account for that. But it's observed that bromine is very selective for the tertiary product. You'll get, 19,000 to 200 to 1. So that's pretty good. If I'm doing my math right, that's about 99% to 1 or something like that. In contrast, chloride or chlorine radical is way less selective, 6 to 4 to 1. Okay? So what's the rationale for this? Well, the rationale is that chlorine is, as a radical, is more reactive than bromine, and you can figure that out by comparing bond energies. It takes more energy to break the chlorine-chlorine bond than it does the bromine-bromine bond, and therefore the chlorine radical is higher in energy. So let's use the color, red for chlorine and blue for bromine in an energy diagram. Chlorine radical plus the starting material starts out higher in energy and is more exothermic, so it goes to products here. Let's see. No, gotta be careful. We're talking about the hydrogen abstraction step. So this would be going from a chlorine radical to a carbon-centered radical. You get HCl and then the carbon-centered radical. And because of this, the transition state and the starting material are close in energy, which means that the structure of the product, thanks about that. Okay, Apple Pencil battery is low, maybe we'll survive. The structure of the product radical doesn't influence the structure of the transition state very much, okay? So if that's the case, then it shouldn't matter whether the product radical is a secondary, primary, or tertiary, because the transition state doesn't look very much like a carbon-centered radical, it looks like a chlorine radical. In contrast, bromine starts out lower in energy because the Br radical, and I don't know how much lower in energy, so whatever. We'll just pretend it's this. If you find out at some point that I've oversimplified to you, then I apologize. Starts out lower. The transition state is actually closer in energy to the carbon-centered radical. Okay, now these two are close together, so the Br transition state, the transition state for the reaction of bromine radical with the hydrocarbon resembles the carbon-centered radical, and therefore radical stability, the carbon-centered radical stability influences reaction rate. Okay, so it's this reactivity selectivity is based on the Hammond postulate, just like the Hammond postulate doesn't always apply. For the same reasons, this reactivity selectivity principle may not apply. So this is just so you can be critical thinkers in terms of how you read the literature and listen to scientific talks. If somebody uses the reactivity selectivity principle like it applies always and they don't do any further investigations, they haven't been as thorough as they should be, because you don't know if it applies unless you do a number of kinetic experiments. If you just use it without that, then you may be being a little bit sloppy. Okay, questions about that? All right, so confusing kinetic rule of thumb number 3. First was Hammond postulate. Second was the related reactivity selectivity principle. Now, to make things a little bit worse, we have something that's called the Curtin-Hammett principle. People get this one mixed up with the Hammond postulate all the time because Hammett and Hammond are pretty close in terms of spelling and pronunciation. So if you're ever in a doubt and you're ever in doubt about which one you're actually talking about, the way you do this is you just sort of slur the end of that phrase. So you can call it the Hammond postulate and the Curtin-Hammett principle, and then whichever way it actually is, you've sort of said it right. So that's a strategy that was taught to me by Dr. Savage. I now pass it on to you, and you can pass it on to your scientific children as the time comes. What is the Curtin-Hammett principle? Well, it relates to a particular situation, and this is a situation in which you have two intermediates that interconvert, and one is slightly higher in energy than the other. And then that equilibrium is rapid, each goes on to irreversibly form product. Intermediate 1 leads to product 1, intermediate 2 leads to product 2. Now, and we're assuming that this energy difference between transition state 1 and product 1 and the difference in energy between transition state 2 and product 2 are high enough such that the reverse reaction is irreversible. That's funny. The reverse reaction is irreversible. The forward reaction. Yeah, let's try that again. The forward reaction is irreversible. The backward reaction is impossibly slow. Or imperceptibly slow may be the better word, okay? This is important because when a reaction's irreversible, we're not going to worry about the influence of the stability of the products on what happens in the reaction, because it doesn't matter, right? Product stability only matters in an equilibrium. If you can't go backwards once you've formed something, then the stability of the product doesn't matter. So the Curtin-Hammett principle says that the outcome of this reaction, the major product of the reaction, is the one that goes through the lower energy transition state. Okay? So the product ratio in the end let's see, sorry. The ratio of product 2 to product 1 depends mostly on the relative reaction rates or the relative transition state energies, where the product that passes through the lowest energy transition state is the major one. Okay? So the Curtin-Hammett principle says that when two intermediates are in equilibrium, and that equilibrium is rapid because the barrier between the intermediates is low, it actually doesn't matter which intermediate is more stable. The product that comes from the lowest energy transition state will be the major product. You might, and it seems rather easy, but it's surprising how many times chemists get this wrong, because we intuitively will say, oh, well, intermediate 2 is more stable and therefore product 2 should be the major product. Not so, right? Because this equilibrium is rapid. And so the only thing that matters is which is the fastest reaction. We'll go over the lowest barrier, and as soon as we do, whatever disappeared is going to be replaced immediately by interconversion of intermediate 2 back to intermediate 1. Now, your text shows you that you can actually show this relationship mathematically. The ratio between the products should equal. And the equilibrium between the two intermediates actually does matter. But the major contributor is the reaction rates. So rate of reaction 2 versus rate of reaction 1. And the major contributor is this difference in reaction rates. Equilibrium matters a little, but reaction rates matter a lot. So what's an example of this Curtin-Hammett postulate? Let's see. We're going to talk about a nucleophilic addition reaction. We're going to be looking down a carbon-carbon bond between a carbonyl carbon and an sp3 hybridized carbon in the back. We won't worry about whether this is an aldehyde or a ketone. And then that sp3 hybridized carbon in the back, we're going to say, is attached to 3 different groups that are small, medium, and large. Except I want to make sure I'm following the notes, so it was small, large, and medium. Who cares? So we might show a number of different conformations for this molecule. Maybe one in which small is here and medium is here and large is here. Maybe a third one, a third sort of conformation in which medium is here, small is here, and large is here. And there is some equilibrium between these conformations. And this is rotation around a carbon-carbon bond. And we've seen before the barrier to this kind of thing is, whoops, forgot. What did we learn in, what did we learn for butane? I forget what the transition state is. The eclipsed conformation for butane. I think it's something like 6, we'll just say 6 kilocalories per mole, the barrier between these two. So let's not even say that because it's not a bond between two sp3 hybridized carbons. It's more complicated than that. Let's just say that interconversion is fast, which of course we know it is at room temperature, right? It's easy to spin methyl groups at room temperature. Because that interconversion is fast, we actually don't need to worry about which is the major conformer in solution. We just need to worry about which transition state is lower in energy. So we could imagine a nucleophile coming in, and remember that attack of sp2 hybridized carbons at carbonyls typically happens from this angle. We'll maybe learn about that later. It's called the Berge-Dunitz angle. So you have to consider the approach and which pathway is better for a nucleophile to approach. Is it better to approach via the small group, the large group, or the medium group? So we only need to, and then this reaction is irreversible. So we only need to worry about which transition state is lower in energy. This is the lowest in energy. This would lead to the lowest in energy transition state. So this reaction is fastest. And the major product would be one with the following stereochemistry, in which, your nucleophile was here, medium, large, and small. That may not be the most stable conformation. You can go back and convince yourself that attack via one side versus the other would lead to a different diastereomeric product. And anyway, this is an illustration of the Curtin-Hammett principle because the equilibrium between conformations didn't matter, only the rate of the reaction, only the energy of the transition state. All right. Anything else we need to say there? Okay, so that was 3. There's 2 others that don't require a lot of explanation. 4 is the principle of microscopic reversibility. And that is if you have a starting material and it goes through a transition state to a product, we'll call in black the forward path. The backwards path has to exactly coincide with the forward path. In other words, you can't propose that a product goes back to starting material through some alternative, right? Because why would it do that? It has this other exactly backwards path it could take that's lower in energy. So the forward and reverse reactions have to be geometrically the same. It's just like you press rewind. Okay, so that doesn't require a lot of explanation. Sometimes people use that in interesting ways to rationalize the results. And then principle 5 is kinetic versus thermodynamic control. 2 basic ideas here. A, if the reaction is equilibrating between various products and the starting material, the most stable product wins. Classic example of this is hydration or dehydration of alcohols to give alkenes. You get the most stable product, right? You get the most stable alkene product. Principle B is if a reaction is irreversible, product stability doesn't matter. Fastest product to form, meaning the one that goes through the lower energy transition state, wins. Okay. Classic example of this is formation of enolates. Under really irreversible formation of enolates with lithium diisopropyl amide under really low temperature conditions. You get the least sterically hindered but less stable enolate. But it doesn't matter that it's less stable because it's the first one you get and you don't go backwards. Okay? So those are some very important things to remember that will help you as you try to think through the effects of organic reactions. A final, I lied. I inadvertently omitted something that was coming because I forgot about it. Sorry. I have to be very careful with my language. If I say I lied, then my children are going to like, well, you didn't tell the truth one time, Dad. Son, what is it, Moroni said something about not taking us to task because of our imperfections, but rather be grateful that you've learned to be wiser than we have been. Teenagers already think they're wiser than you, though, so it's not. Okay, so effective molarity is a concept that says basically intramolecular reactions are faster than intermolecular reactions. And that sort of seems duh. I mean, it's related to the pre-organization principle that I talked about in my seminar a couple weeks ago, that if you already have two things connected, they don't have to find each other. And so the reaction rate should be faster. But this is an interesting problem in macrocyclization. And some of you may be making macrocycles in your graduate career, and it's an interesting problem. Let's imagine we have molecule I. I don't know why we're calling it I, because maybe we like the imaginary unit. And you've got an amino group and an iodo group, and you can go through this intramolecular pathway, which we're going to call pathway 2. Why do we need to use Roman numerals? We don't. That's just confusing. This is the intramolecular pathway, and you end up with the cyclized compound and the iodo leaving group. And then we'll call pathway 1 the intermolecular reaction, where two molecules of I react together to give you a longer polymer. Right, see what we've done? We've taken one of these and had it displace the iodide on the other. Which should be the major product. And you could go on to make additional units, or additional sort of polymers. But if we look at the rate, and we'll call this the cyclic form, and we'll call this the linear form. The rate of the cyclic form should be rate constant K2 times the concentration of I. In contrast, the rate of the linear form, at least that first step, should be K1, but it should be related to the square of the concentration I, because you need two of those in the reaction step, not just one. So you can see that the linear reaction will depend a lot on the concentration, and the cyclic reaction will depend a lot less on the concentration. So we need to leave it there today, but I'll show you how you take these two reaction rates and actually get an idea of what's called effective molarity. That is, how pretend concentrated are these two things now that they're close to each other? And it's a good way of thinking about how to get a cyclic product versus a linear product. So we'll pick that up next time. And then we're going to get into differential equations and analysis of complex reaction mechanisms. So be prepared for some maths.